Have you ever had one of those days where um, a tiny, almost insignificant decision you made early in the morning somehow cascaded into a totally unexpected, maybe even chaotic outcome by the evening?
Oh, absolutely.
Yeah.
Or you marvel at how, you know, a single cell somehow develops into something as incredibly intricate and functional as a human eye.
Yeah, it feels like there's some kind of invisible hand at play, doesn't it? Something that just defies simple cause and effect.
Exactly. And that feeling, that sense of like immense unpredictable outcomes coming from seemingly small beginnings.
Yeah.
Well, it isn't just about things being complicated.
No, it's about something far more profound, something that really underpins everything from our brains to, well, the vast swirling galaxies. It's about complexity.
Precisely. And we often use complicated and complex almost interchangeably in everyday chat, right?
Yeah.
But in the realm of systems, they are fundamentally, crucially different concepts.
Okay.
So today, our mission on the deep dive is really to unpack what complexity truly means, how it shows up across fields that seem totally unrelated.
And why understanding it is maybe a shortcut to making sense of this incredibly dynamic world we live in.
That's the goal. We've sifted through a pretty fascinating stack of sources for you, looking into cutting-edge research. That includes recent explorations into things like hyperspace physics and a particular theory of everything.
The HHHCR TOE framework.
Yeah, that one. Which, look, it's highly theoretical, obviously, but it offers this unique sort of multi-layered lens to view these complex systems. And we can pull out some, well, surprising nuggets of insight for you.
Okay, let's unpack this. So when we talk about complexity, it's way more than just a fancy buzzword for really, really hard to understand.
Right.
Our sources give us a more formal definition, something we can build on. It goes, complexity refers to the characteristic of a system or process that consists of many components which interact in multiple and intricate ways, resulting in emergent behavior that is difficult to predict.
Sounds a bit academic, maybe.
It does, a little, but let's break it down. Because grasping the real practical difference between something merely complicated and something genuinely complex, well, it's huge.
It really is. It can fundamentally change how you approach problems, whether that's like managing a team or trying to figure out global events.
So how do we draw that line clearly?
Okay, think of it this way. Consider a modern jet engine. It is, without a doubt, incredibly complicated, isn't it?
Absolutely. Thousands of parts, wires everywhere.
Exactly. Thousands of parts, intricate wiring, precision machine gears, fuel lines, hydraulic systems, all designed with astonishing precision. Now, if something goes wrong with that engine,
An expert can fix it.
right, an expert mechanic can, given enough time, the right tools, the schematics, they can take it apart, analyze every single component, understand exactly why it failed, fix it, put it back together.
And you know it'll work as expected.
You can be confident it will perform exactly as expected. Why? Because its behavior is predictable. It's fully understandable by analyzing its individual components. That's the essence of complicated. It's reducible, knowable, and ultimately controllable. You can model it with really high accuracy.
Okay, complicated equals reducible, predictable. Got it. But then the weather.
Ah, yes, the weather. Now, imagine trying to predict next month's weather with perfect accuracy.
Forget it.
Right. The precise temperature, wind speed, precipitation for every single day, everywhere. Even with all our supercomputers, all our satellites, all our data, it's still practically impossible.
Why is that? I mean, it's just physics, right? Air moving around.
Well, yes and no. It's because the weather isn't just complicated. It's a deeply complex system. It has countless interacting components,
Yeah.
massive air currents, fluctuating ocean temperatures, varied land masses absorbing and radiating heat differently.
Full radiation, dust particles.
Even microscopic dust particles in the atmosphere. These interactions are so intricate, so numerous, and involve so many interwoven feedback loops that even tiny, almost immeasurable changes in one part of the system.
Like a butterfly flapping its wings.
That's the classic idea, the butterfly effect. Over time, those tiny changes can cascade into massive, unpredictable effects across the entire globe. A hurricane forming, a sudden cold snap.
You can't predict that by looking at one air molecule.
Exactly. That's the key here.
Yeah.
The whole system exhibits emergent behavior that you simply cannot understand by looking at individual air molecules or isolated ocean currents. The whole is truly profoundly greater than the sum of its parts.
And that distinction is vital, you're saying, because it shifts your approach.
Completely. You move from trying to control every individual piece, like in the jet engine, to understand the dynamics, the interactions, the patterns of the system itself.
Okay. So that distinction between complicated and complex is crucial then, not just for engineering, but biology, economics.
Absolutely. Biology, economics, social systems, ecosystems,
Yeah.
you name it. A truly complex system, unlike a merely complicated one, shows properties you just won't find in any of its individual components.
These are the properties that emerge from the interactions?
Precisely. They emerge. And this leads us right into the core characteristics that define these complex systems. And these are worth dwelling on because they really explain why our world behaves the way it does.
All right, let's list them out. First up.
Interconnected components. In a complex system, nothing truly operates in isolation. It's not just that there are many parts, it's that they are highly interconnected.
Like a network.
Exactly, often with intricate networks of relationships and, crucially, feedback loops. Imagine a vast social network. What one person shares influences dozens, who then share it further, creating ripples.
Or the brain, right? Trillions of connections.
The human brain, yes. Or think about a global supply chain. A disruption in one tiny part of the world can instantly affect consumers continents away. The output of one component constantly becomes the input for another. It's this dynamic, flowing loop of interaction.
Okay, interconnectedness. What follows from that?
Well, this dense interconnectedness directly leads to our next characteristic, emergence. This is where those new, often surprising, and utterly unpredictable properties arise just from the interaction of simpler parts.
Like consciousness from neurons.
Consciousness is the perfect example. It's an emergent property of billions of individual neurons firing and connecting in complex ways. No single neuron is conscious, right? Nor is a small cluster.
But put them all together.
Put them together in this incredibly complex interacting network, and boom, you get the astonishing phenomenon of consciousness.
It's like a symphony. Individual notes are simple, but together.
That's a great analogy. Individual notes are just simple vibrations, but their complex arrangement and interaction create this profound, emergent musical experience that absolutely transcends any single note.
So it challenges that whole reductionist way of thinking, just breaking things down.
Completely. It forces us to look at the whole system, the interactions, not just the isolated parts.
Okay, what else characterizes these systems?
Then we have adaptive behavior. Many complex systems, especially living ones, aren't static. They're not locked into a set pattern.
They change.
They're dynamic. They evolve and respond to changes in their environment. Think about an ecosystem. The species within it aren't just reacting passively.
They don't.
Constantly adapting to shifting climates, new competitors, new food sources. They modify their behavior, even their physical traits, over generations. It's this ongoing dynamic dance of adjustment.
And that's what allows them to survive in unpredictable worlds.
Exactly. That adaptive capacity is crucial for survival and thriving.
All right. And linking back to the weather example you mentioned.
Non-linearity,
Yeah.
yes. This is where small changes can indeed have those large, disproportionate, and often unpredictable effects we talked about.
Yeah.
The butterfly effect again.
Cause and effect aren't straightforward.
Rarely proportional or simple in complex systems. Doubling an input doesn't necessarily double the output, might quintuple it, or negate it entirely, or send the whole system off in some completely unexpected direction.
Like a social media trend. A small post goes viral.
Perfect example. A seemingly minor post suddenly gains unforeseen momentum. Or think about a small policy change in a large organization. It can ripple out and lead to massive unintended consequences throughout the whole company.
And that non-linearity is why prediction is so hard.
It's a primary reason, yes. Complex systems resist simple prediction because of it.
Okay, interconnectedness, emergence, adaptation, non-linearity. What else?
This nonlinearity, combined with their deep interconnectedness, leads us naturally to dynamism. Complex systems are rarely in a steady, static state.
They're always changing.
Constantly evolving, constantly changing over time. They might never actually reach a true equilibrium. The global climate system, again, is a prime example. It's dynamic, with intricate, constantly shifting patterns that prevent it from just settling down into some predictable, stable state.
Like a city, traffic, economy, social stuff, always in flux.
Exactly like a city. This constant change means that understanding a complex system requires observing its behavior over time, not just looking at a single snapshot. You need to see the movie, not just the photo.
Makes sense. And the last key characteristic.
And finally, maybe the most captivating one, self-organization. This is the incredible ability of some complex systems to spontaneously organize themselves into intricate patterns or structures.
Without a leader, without instructions.
Without any external guidance, central control, or explicit programming. Think about a flock of birds. Those breathtaking murmurations in the sky, who's telling them how to do that?
Nobody, they just do it.
They just do it. Simple individual rules like stay close to your neighbor but don't collide lead to incredibly complex, organized collective behavior. It just emerges.
That's fascinating. What does that tell us?
Well, this principle is crucial for understanding how, say, decentralized organizations can succeed, or how social movements gain momentum without a single figurehead, or even, potentially, how consciousness arises from individual neurons acting locally.
So sometimes top-down control isn't the answer.
Sometimes, the best way to foster order isn't through rigid top-down control, but by setting up the right conditions, the right simple rules, for order to emerge naturally from the bottom up.
Wow. Okay, so the way these characteristics, interconnectedness, emergence, non-linearity, dynamism, self-organization, the way they all weave together,
Yeah.
that's what makes complexity so tricky, but also so important to grasp.
Absolutely. Nonlinearity plus interconnectedness equals hard-to-predict dynamism. And self-organization is this powerful manifestation of emergence, where amazing order arises from local interactions, no grand designer needed.
It really does reshape how you think about cause, effect, and control.
It has to. And building on that, complexity isn't just one single thing. It shows up in different ways, right? Leading to various categories of complexity across different fields.
Okay, like what?
Well, for instance, there's deterministic complexity. These are systems governed by underlying rules, often simple ones, where, in principle, you could predict the outcome if you had perfect knowledge of the starting conditions and infinite computing power.
Okay, in principle being the key phrase there.
Exactly. Our sources mention chaotic systems like, yes, weather patterns again, or something like the double pendulum, that fascinating physics demonstration.
Right, the one that swings totally unpredictably.
Precisely. These systems follow deterministic rules. Physics dictates their every move. But they are so incredibly sensitive to their initial condition
Tiny changes blow up.
that even the tiniest immeasurable difference at the start leads to wildly divergent, unpredictable outcomes very quickly. Change one tiny starting variable by an infinitesimal amount, and the outcome just diverges almost instantly. So, theoretically predictable.
Yeah.
Maybe. Practically. No way.
Okay, so that's deterministic complexity. What else?
Then you have stochastic complexity. This type inherently introduces randomness and probabilistic outcomes. Here, precise prediction is fundamentally impossible because chance itself plays a role.
Like rolling dice, but on a massive scale.
Sort of. Think about the seemingly random fluctuations of stock market prices. Yes, there are underlying trends and rules, maybe, but individual movements can be influenced by countless random events, sentiments, news.
Or particles bouncing around.
The diffusion of particles in a fluid, yeah. Each particle's path is subject to random collisions. Understanding these systems requires a probabilistic approach, thinking in terms of likelihoods and distributions, not exact outcomes.
Got it. Deterministic, stochastic. But what about living things?
That brings us to biological complexity. This specifically relates to living systems, at all scales. The human immune system is a fantastic example.
How so?
Think about it. Multiple layers of interacting cells, proteins, complex signaling pathways, feedback loops. It provides these incredibly adaptive defense mechanisms against an ever-changing array of threats like bacteria and viruses.
It learns, right?
It's a marvel of self-organization, adaptation, and emergent intelligence operating at a cellular level. It learns and evolves as it encounters new pathogens. Or think about how a forest ecosystem responds to a drought or a fire that demonstrates immense biological complexity too.
Okay. And one more category you mentioned.
And finally, for our discussion today, there's epistemic complexity. This is a bit different. It concerns the challenges in understanding a system.
Not because the system itself is random, but because we can't grasp it.
Exactly. It's because we have incomplete information, or there are hidden variables we don't know about, or we just have fundamental limitations in our ability to collect data or measure things accurately.
Like mapping the entire human brain.
Trying to fully map the brain, understand every single neural connection and its firing pattern in real time, that's epistemic complexity.
Yeah.
Or trying to comprehend large-scale global economic systems where you can never know or measure all the variables perfectly.
So the system might be deterministic or stochastic, but for us, it's complex because we can't get all the info.
Precisely. It's a complexity of knowing, a limit on our knowledge, rather than a necessarily inherent randomness or chaos in the system itself.
And these categories, deterministic, stochastic, biological, epistemic, they're not neat boxes, are they?
Not at all. What's fascinating is how they often overlap and interweave in real-world systems. A biological system, for instance.
Might have some deterministic chaos, some random mutations, and we definitely can't measure everything.
Exactly. It might exhibit deterministic chaos in certain physiological processes while also dealing with stochastic elements like random genetic mutations.
Hmm.
And it absolutely presents epistemic challenges because we can't possibly measure everything happening inside a cell or an organism simultaneously.
So it really highlights how complexity science has to pull from everywhere. Physics, biology, computer science.
Mathematics, sociology, even philosophy. It's inherently interdisciplinary. It acts as a kind of unifying lens across all these different domains.
Okay, so complexity is everywhere, manifesting in these different ways, from weather chaos to the limits of our own knowledge.
Hmm.
But this raises a big question.
Which is?
How do these incredibly intricate systems manage to persist, to evolve, to even defy what seems like the natural tendency for everything to fall apart? Entropy.
Ah, yes. How do they sustain themselves? That's where it gets really interesting as we dive into the fundamental factors that seem to drive and sustain complexity, pulling again from our source material on these cutting-edge theories.
Right. And this brings us to a concept that might sound a bit like science fiction, but you're saying it's a very real and crucial, negentropy.
Negentropy, or sometimes called negative entropy. Now, you're probably familiar with entropy, right?
Yeah, the universe's tendency toward disorder. Things break down, energy spreads out, my coffee getting cold.
Exactly. Energy disperses, structures break down, things generally fall apart over time. Like an old building decaying or that hot cup of coffee cooling down to room temperature. Negentropy is the active counterforce to that.
So it's not just resisting disorder, it's creating order.
Precisely. Our sources define it as the process of creating and maintaining order, increasing structure, and actively reducing disorder within a system. It's about actively building and maintaining order by leveraging energy and information.
And this is seen as a key driver within those theoretical frameworks like the HHHCR-TOE.
Yes, within frameworks like that, negentropy is viewed as a fundamental driver for complexity. It actively counters chaos. It promotes self-organization and the emergence of structured, highly organized systems from less ordered states.
How does it do that?
Well, the idea is that this is how complex systems can harness and channel energy more effectively, allowing them to build and maintain incredibly intricate structures, often far from simple thermodynamic equilibrium.
Like life itself, life seems like a constant battle against breaking down.
Think about it. Life is a constant, astonishing battle against entropy. The universe's relentless push toward disorder. Negentropy is that active force allowing complex systems, like us, like ecosystems, to build and maintain incredible order and intricate structures, from the DNA helix all the way up to the entire human body or a rainforest.
And our sources connect this to information theory, Claude Shannon.
They do. There's a connection where information itself can be seen as a measure of negentropy. The more information a system processes and utilizes in an organized way, the more ordered and less entropic it becomes.
Like a library versus a random pile of books.
Perfect analogy. A well-organized library, high information, high negentropy, is far more useful, far more ordered than a random pile of books, low information, high entropy. The very act of processing, storing, and using information allows systems to maintain structure and function, effectively pushing back against that tide of disorder.
So the persistence of life and intelligence over billions of years, that's negentropy in action.
It's a prime example of negentropy in powerful, ongoing action, defying those entropic forces.
And the HHHCR-TOE takes this even further.
Well, within that specific framework, negentropy is suggested to drive processes that support what's called coherence and resonance among the system's components.
Meaning they work together better, more stable.
Kind of. It means they act together in a more synchronized and stable way. It's almost like proposing a fundamental building code from the universe itself for creating stable complexity. It offers a theoretical basis for why certain complex systems, like life or intelligent systems, can persist and even flourish against that universal push towards disorder.
It suggests the universe might actually favor creating complexity under the right conditions.
That's the implication, yes, that the universe might inherently favor the formation of such complex ordered systems driven by this digentropic principle.
Okay, negentropy as an ordering force. What's the next driver?
Next up, we have symmetry and symmetry breaking. Now, symmetry, at its simplest, just means invariance under transformations.
Like a snowflake. Rotated, it looks the same.
Exactly. It looks the same from different perspectives or after certain operations. It often implies a uniform, maybe simpler state. But then there's symmetry breaking.
Breaking the pattern.
It's the transformative process, where a system transitions from an ordered, simpler, often symmetrical state to a more complex, differentiated one precisely by losing a previous symmetry.
Losing symmetry leads to more complexity. That sounds backward.
It does sound counterintuitive, doesn't it?
But
But what's fascinating about this breaking isn't that it leads to disorder. Often it's a fundamental driver for diversity, for increased interactions, and for the emergence of new, more intricate structures.
how does the HHHCR toe view this?
Within that theory, symmetry breaking is seen as a dynamic shift from one coherent state to another. And this shift allows entirely new structures and stable systems to emerge and persist.
Can you give an example?
Think about the very early universe, incredibly hot, incredibly dense, and incredibly symmetrical. Almost a featureless soup of energy, very uniform. But as it expanded and cooled, fundamental symmetries were broken. This led to the formation of distinct particles, quarks, electrons, then atoms, then stars, galaxies. Each symmetry-breaking event was a step towards increased complexity and new stable configurations. It drove the universe's evolution from simple uniformity to the rich structure we see now.
And this happens on smaller scales, too.
Oh, absolutely. Everywhere. Think about water freezing into an ice crystal. Liquid water has a high degree of symmetry. It looks pretty much the same no matter how you turn it or where you look within it.
Right, it just flows.
But when it freezes, it forms a specific crystalline structure, like a snowflake or just a block of ice. That structure breaks some of the liquid's continuous symmetry by imposing a rigid, ordered lattice. But the result is a more ordered, intricate, and structurally complex system than the liquid was.
Or like an embryo developing. Starts symmetrical.
A fertilized egg cell, yes, initially quite symmetrical. But as it develops, it undergoes repeated symmetry-breaking events. Cells differentiate, specialize. This leads to the formation of specialized tissues, organs, eventually creating a complex, highly asymmetrical organism.
So breaking symmetry creates the building blocks for complexity.
It allows for differentiation and specialization, which are essential for complex structures. And our sources highlight that life and intelligence don't seem to maintain a static, rigid symmetry. Instead, they exhibit what's called adaptive symmetry.
Adaptive symmetry.
Yeah, it's like a dynamic balance of energy and coherence that allows for incredible resilience and adaptability. They can maintain core functions while still changing and responding. Mathematically, you can even describe this with things like potential functions, shifting the system from a symmetric state to a broken symmetry one, leading to new configurations and increased complexity.
So it's the mechanism allowing diverse structures and behaviors to emerge from simpler beginnings.
Exactly. It creates the rich tapestry of complexity we observe all around us.
Okay, this next one sounds really counterintuitive. Coherence resonance. You mentioned noise-induced order.
Yes, this is where it gets truly fascinating and surprisingly powerful. Coherence resonance is this phenomenon where a system actually achieves optimal order in synchronization, not by eliminating noise, but through the perfect interplay.
An interplay between what?
Between a weak external signal or forcing, the system's own internal dynamics, and crucially, a certain optimal amount of internal noise or random fluctuations.
So noise helps create order. That sounds like a paradox.
It absolutely sounds paradoxical. But it's a well-observed phenomenon in many systems, from physics to biology. It allows systems to harness and maintain order, despite what we typically think of as disturbances or randomness.
How does that work? Can you give an analogy?
Okay, imagine trying to hear a really faint, almost inaudible radio signal in a room that is completely, absolutely silent. Sometimes it can actually be very difficult to pick out that whisper of a signal against pure silence.
Right, your ears strain, maybe?
Exactly. But now, introduce a gentle, steady hum of background static. Not too much, not too little, just the right amount. Suddenly, that faint whisper of the radio signal might become clearer.
The noise helps you hear the signal.
In a sense, yes. That optimal level of background noise can actually help synchronize your perception, maybe boosting the sensitivity of your auditory system, allowing your brain to better pick out the weak signal from the subtle variations in the noise. That's a simplified way to think about coherence resonance.
So it's like the noise amplifies the system's ability to respond to a weak signal.
Or helps different parts of the system synchronize their response to that signal. Think about neurons in your brain. Individual neurons might fire somewhat sporadically on their own,
Right.
but a certain level of background noise in the neural network, random fluctuations in membrane potentials, maybe, or a specific amount of external sensory stimulus, can actually help synchronize their firing patterns.
Making them fire together.
It can lead to more coherent, rhythmic brain activity, which we know is essential for processes like perception, attention, memory, even conscious thought. This leads to what's called phase synchronization, where multiple components, like neurons, start to oscillate in harmony, creating a larger, more organized pattern out of what might have seemed like noisy chaos.
So sometimes a bit of controlled chaos is actually needed for the system to find its optimal rhythm or state.
Exactly. It's not that noise is always good, but that there can be an optimal level of noise that enhances the system's orderliness or its ability to detect weak signals.
How does this fit into the bigger picture theories?
Well, this concept is deeply integrated into advanced theories of complexity. Within our HHHCR Toki sources, for example, it's connected to how resonance effects might propagate and contribute to emergent order across vast scales, even in these hypothetical hyperdimensional systems.
So the universe itself might use this trick.
It suggests the universe might leverage this principle, finding that sweet spot where external fluctuations or internal noise are effectively channeled to achieve internal stability and coherence in complex structures. It really challenges that traditional view that noise is always detrimental, always something to be eliminated. It reveals its surprising constructive potential.
Fascinating. Okay, moving from noise to structure. Fractals and multi-scale structures, these seem to pop up everywhere in complex systems.
They really do, from the very small to the very large. We're talking about patterns within patterns, structures characterized by self-similarity.
Meaning the same pattern repeats at different scales.
Exactly, like a tree. The way the trunk branches into major limbs, then those limbs branch into smaller branches, then those into tiny twigs, essentially the same branching pattern, just repeating at different sizes. It exhibits what's called scale invariance.
And they have weird dimensions, right? Not just 1D, 2D, 3D.
Yes, a key aspect is their non-integer fractal dimension. It's a numerical measure of their complexity, how wrinkled or space-filling they are. A straight line has dimension 1, a flat square is 2, a solid cube is 3.
But a coastline.
A coastline, which is jagged and irregular no matter how closely you look, might have a fractal dimension of, say, 1.26. It means it's more than just a line, but it doesn't completely fill a 2D plane.
And why are these fractal structures so common in nature?
Because they are incredibly efficient designs, often optimized by nature, through evolution perhaps, for processes like energy flow, resource distribution, or maximizing surface area across vastly different scales.
Like in our lungs.
Your lungs are a brilliant biological fractal. The way your windpipe branches into smaller and smaller airways, the bronchi, then bronchioles, all the way down to the tiny air vacs, the alveoli, it's a classic self-similar pattern.
And that maximizes the surface for oxygen exchange.
Hugely maximizes it in a compact space.
Yeah.
It's an incredibly efficient design for gas transfer. Similarly, think about the intricate branching of our blood vessels delivering oxygen and nutrients everywhere, or our nerve networks reaching every part of the body.
Or a fern leaf, a snowflake, river systems.
The patterns of a fern leaf, the intricate beauty of a snowflake, the way rivers branch across a landscape, all stunning natural fractals. And what's really fascinating is that similar fractal patterns appear in completely different contexts, too.
Like where?
Like the structure of the internet's connections, the distribution of galaxies in the universe, or even, some studies suggest, the fluctuations in stock market prices over different timescales.
It seems like a universal design principle for efficiency and coverage.
It really does.
Right.
And within our sources, particularly the more theoretical ones like HHHCR this concept gets extended to hyperfractal geometry.
Fractals in higher dimensions.
Kind of, conceptualizing how these self-similar patterns might manifest universally, perhaps linking the quantum scale, the micro, to the cosmic scale, the macro. The idea is that energy distribution within these complex systems often follows power law behavior,
Meaning?
meaning a small number of elements or events account for a large proportion of the energy, influence, or size, while most elements are much smaller or less influential. Like earthquakes, lots of small tremors, very few massive ones. This power law distribution, often linked to fractal structures, allows for incredibly efficient channeling of resources and information across vast differences in scale, optimizing performance in environments from the quantum foam all the way up to galactic clusters.
Wow. Okay, one more key driver. Feedback mechanisms. These sound crucial for regulation.
Absolutely critical. These are the processes that allow systems to respond to internal and external changes. They facilitate self-regulation, adaptation, and the emergence of highly complex behavior.
It's like the system talking to itself.
Yeah.
Checking its own output.
That's a great way to put it. It's the system's ongoing internal dialogue, constantly checking and adjusting itself based on its own performance or the environment's response.
And there are different types of feedback.
Broadly, we can differentiate between two main, often intertwined, types. positive feedback and negative feedback.
Okay, positive feedback. That sounds good.
Not always. Positive feedback amplifies changes. It leads to growth, reinforcement, or sometimes rapid roadway transformation. Think of population growth. More individuals lead to more births, which means even more individuals. It's an exponential curve, amplifying the initial population.
Or a microphone squealing near a speaker.
Classic positive feedback loop. The sound gets amplified, feeds back into the microphone, gets amplified more. Or think about signals in a neural network. A strong initial signal can cause many more downstream neurons to fire, amplifying the input. In a forest fire, a small fire dries out surrounding vegetation, making it more flammable, which helps the fire grow larger and more intense. It drives change, sometimes explosively.
Okay, so positive feedback amplifies. What about negative feedback?
Negative feedback, in contrast, counteracts changes. It works to stabilize the system, maintain equilibrium, or what biologists call homeostasis.
Like a thermostat.
Your body temperature regulations is a perfect biological example. If you get too hot, your body automatically triggers sweating to cool you down, counteracting the rise in temperature. If you get too cold, you shiver to generate heat.
It brings things back to balance.
Exactly. Or the thermostat in your house, it kicks on the AC when the temperature rises above the set point and turns it off when it cools down below it, maintaining a relatively stable temperature range. It's all about maintaining balance, resisting deviation. In a company, regular performance reviews, if done well, can act as negative feedback, helping correct deviations from goals.
So you need both. Positive to grow and change, negative to stay stable.
The dynamic interplay between these two types of feedback is absolutely essential for sustained complexity and adaptive behavior. You need positive feedback to push for change, growth, innovation, adaptation, but you need negative feedback to prevent runaway effects, damp down oscillations, ensure stability, and stop the system from just collapsing or spiraling out of control.
It's a constant balancing act.
A constant, delicate, and often quite dynamic dance between pushing boundaries and maintaining internal balance. This dynamic is what allows complex systems to successfully navigate unpredictable environments over long periods.
And these feedback loops are also central in those advanced theories.
Absolutely. In frameworks like the HHHCR TOE, feedback mechanisms are seen as integral to maintaining coherence and stability across even highly complex, multi-layered, interconnected systems. They talk about feedback operating across dimensions, suggesting interactions far more complex than simple linear cause and effect.
Okay, so we've explored how these systems manage to build and sustain themselves, negentropy fighting disorder, symmetry breaking creating structure, coherence resonance finding order in noise, fractals providing efficiency, and feedback enabling regulation. It's quite a toolkit.
It really is. A toolkit the universe seems to use quite effectively.
But now, what does all this mean for the really big questions? What happens when we start applying these principles of complexity to understand life itself, and maybe even to the cutting edge of artificial intelligence?
Right. This is where our sources point towards a potentially grand unifying vision.
Which is?
The fundamental idea here is that complexity isn't just a descriptive term, a way to categorize things we find difficult. It might actually be a profound organizing principle, something that underlies the hidden patterns of life, of evolution, of cognition itself.
So a unifying theory connecting biology, AI, life. It has to be built on understanding complexity.
That's the argument. It must fundamentally understand how complex systems encode information, how they process it, how they evolve that information to create adaptive and intelligent structures.
Yeah.
This kind of approach starts to bridge fields that seemed totally separate before.
Showing common threads running through them all.
Exactly. Showing that there are common universal threads woven throughout, from the smallest biological processes happening in your cells right now to the most advanced AI being developed.
And it's incredible when you start looking for those connections. Our sources emphasize that you find the same kinds of hidden patterns everywhere.
Like what?
Like fractal structures, intricate feedback loops, recursive processes. You find them in DNA sequences. You find them in the algorithms that drive biological evolution. You find them in the neural circuits in our brains.
And now, increasingly, in the architectures of AI.
Right. It's like this universal language of organization. It suggests a deep underlying unity in how complex systems emerge and operate, whether they grew naturally or we built them artificially.
So let's dive into those common threads a bit more, the ones that seem to bridge biology, AI, and life itself, starting with complex information processing.
DNA seems like the obvious biological example.
It's a prime example, yes.
Yeah.
DNA is an incredibly complex information system. It's not just a simple static blueprint. The sequences of code in DNA.
Lead to astonishingly organized biological structures.
Exactly. And crucially, these structures adapt and evolve through intricate, multi-layered feedback loops involving how genes are expressed, how proteins interact, how the environment signals back to the cell. DNA doesn't just encode linear instructions. It interacts dynamically with its environment and with itself in these recursive ways.
And we see parallels in AI.
Clearly, advanced AI architectures like deep neural networks are often directly inspired by the brain's structure, and they process information in remarkably similar, complex ways.
Layers, connections, feedback.
Exactly. They use layers of interconnected nodes, vast networks of weighted connections, and various forms of feedback loops to learn from enormous amounts of data, identify subtle patterns, and make decisions or predictions.
Even evolutionary algorithms.
Evolutionary algorithms in AI explicitly mimic natural selection and mutation. They apply principles of variation, selection, and inheritance to digital solutions, evolving better algorithms or designs over generations.
So this parallel isn't just a coincidence.
It strongly suggests it's not accidental. It highlights that both biological intelligence and potentially artificial intelligence leverage similar fundamental principles of feedback, adaptation, information processing, and optimization to achieve complex goals, whether it's surviving in an ecosystem or mastering a complex game like Go.
Okay, so complex information processing is one thread. What about emergence?
This intricate information processing naturally leads us back to emergence. Cognition, the ability to think, perceive, learn, understand, whether it's happening in your biological brain or in an advanced AI, is widely viewed as a profound emergent property.
It doesn't live in one place.
It doesn't reside in any single neuron or any single line of code. It arises from the complex, dynamic interactions of the entire system working together.
And those theoretical frameworks try to explain how that happens, like omnilectic logic.
Right. Our sources mention theoretical frameworks like omnilectic logic, potentially within the HHHCR TOE has attempts to formalize this. They try to explain how higher-order coherence and complexity like thought or understanding emerge through these multi-level interactions and recursive feedback loops.
And this logic could apply to both brains and AI.
That's the idea. It could potentially be applied to understanding how neural networks in the brain process sensory inputs to form coherent perceptions, and how sophisticated AI systems adapt and learn through iterative feedback, leading to capabilities that weren't explicitly programmed but just emerge from the sheer scale and complexity of their interactions.
Okay, third thread. Feedback and self-organization. We touched on this, but how does it bridge biology and AI?
Well, life's remarkable ability to self-organize, what biologists sometimes call autopoiesis, the system's capacity to reproduce and maintain itself, is a defining hallmark of all complex living systems.
Like individual cells managing themselves.
Individual cells are miniature marvels of self-organization. They constantly regulate their own gene expression, manage intricate metabolic pathways, maintain internal balance, all through incredibly complex, interwoven feedback loops that ensure their survival and function without any central controller overseeing every molecule.
And we're seeing similar things in AI now.
Strikingly similar things, yes. In the rapidly advancing world of AI, models employing techniques like deep reinforcement learning or especially generative adversarial networks, GANs, demonstrate remarkable self-organizing behavior.
How do GANs work again?
Think about how a GAN learns. You have two neural networks, basically, a generator and a discriminator. They're pitted against each other in this continuous feedback loop. The generator tries to create increasingly realistic outputs, say, images of faces. The discriminator tries to tell if the images it's shown are real faces or fake ones created by the generator.
They compete and learn from each other.
Exactly. This internal competition and the continuous feedback loop constantly force both networks to refine their abilities. The generator gets better at faking, the discriminator gets better at detecting fakes. This leads to astonishingly realistic images, or even novel creative outputs, emerging without humans explicitly programming every rule for what makes a realistic face.
That is self-organization in action, driven by internal feedback. It mirrors biology.
It really does mirror the adaptive, sometimes creative, and self-correcting processes we see throughout biological systems.
So all these threads, complex information processing, emergence, feedback, self-organization, they seem to point towards a deeper understanding of the essence of life itself.
That's the profound conclusion some of these sources lean towards. Life, in its broadest sense, might be understood as the ultimate complex adaptive system. It evolves, it adapts, it processes information, it self-organizes in ways that continuously create order and novelty, pushing back against simple decay.
So the synthesis of DNA coding, evolution, cognition, it all suggests life's essence is rooted in complexity.
Rooted in complexity's fundamental ability to create and maintain order, to adapt to chaos, and to generate novel emergent properties.
Yeah.
That seems to be the common denominator.
And here's the kicker. As AI gets more complex,
As AI systems become more sophisticated and powerful, they increasingly mirror this biological complexity. They integrate feedback, adaptation, self-organization in ways that reflect the very same universal principles that seem to underlie biological life.
which points to
What?
a deeper unifying principle.
It points towards a potentially deeper unifying principle, yes, where intelligence, whether it's natural or artificial, is fundamentally a product of complex, integrated systems that can effectively process information, learn from experience, and adapt to their environment. It hints that maybe there's a universal recipe for intelligence, and perhaps even for some aspects of what we consider life, that isn't restricted just to carbon-based biology.
Wow. That's a big idea. And these theoretical frameworks like the omnilectic logic or the HHHCR-TOE stuff, they're trying to provide the language for this.
They represent ambitious attempts to build that language, yes. Frameworks like analytic logic are conceptualized as ways to understand the inherently recursive, multi-layered nature of these complex systems. How different, even seemingly contradictory aspects or levels can interact constructively to create a richer, more coherent, functional whole.
What's the potential application of a logic like that?
Well, the potential is immense, though it's still highly theoretical, remember. Such a framework could, perhaps one day, allow us to model intricate biological systems with much greater fidelity, like the precise interactions of DNA folding and gene regulation at a molecular level, or the complex dynamic processes supporting consciousness in neural networks.
And for AI.
Crucially, it could also guide the design of truly adaptive, robust AI systems. AI that more intelligently mimics these natural processes of self-organization and emergence, potentially unlocking entirely new levels of artificial intelligence that are less brittle and more genuinely adaptable than what we have now.
So it's an attempt to unify physics, biology, information.
It's an ambitious attempt to unify physical laws with biological processes and information dynamics, trying to find principles that span the quantum scale, the biological scale, and even the cosmic scale, suggesting a fundamental unity in how the universe designs and builds complex, functional systems.
And you mentioned hyperdimensional interactions within that HHHCR2E. How does that fit?
That goes even deeper, suggesting that the very fabric of space-time and potentially dimensions beyond our everyday three spatial and one time dimension might actually influence phenomena we observe right down at the level of genetic coding, cellular behavior, and even cognitive processes.
So the structure of reality itself enables complexity.
That's the implication. A profound connection between the fundamental geometric structure of the universe and the emergence and evolution of life and intelligence. The idea is that this posited, multidimensional structure of reality might directly impact how complexity arises, how it thrives, and how it gives rise to the sophisticated adaptive systems we observe in biology and increasingly now in AI.
That's audacious. Complexity isn't just a feature of the universe. It's woven into its very blueprint by its dimensionality.
That's the truly audacious idea embedded in some of these theories, yes. That complexity is perhaps a fundamental aspect of the universe's fabric, linking the basic building blocks of existence to the adaptive, sentient, and intelligent systems that arise from them through principles like coherence, resonance, and feedback operating across these posited dimensions. It's an attempt to find the underlying grammar of reality itself.
Okay, so we've covered a lot of ground today. We started by really trying to pin down complexity, making that crucial distinction from just being complicated.
Right, the jet engine versus the weather.
Exactly. Then we walked through the key characteristics: interconnectedness, emergence, adaptation, non-linearity, dynamism, and that fascinating idea of self-organization. Then we dove into the core drivers that allowed these systems to persist and evolve, negentropy pushing back against disorder.
The symmetry breaking, creating diversity, coherence resonance, finding order in noise, fractals offering efficiency, and feedback mechanisms enabling regulation and adaptation.
And finally, we pulled all those threads together, looking at complexity as maybe the core organizing principle that links biology, AI, and maybe even the essence of life itself.
Showing how things like complex information processing, emergence, and self-organization seem to be universal themes, echoed in theoretical frameworks trying to describe reality at a deeper level.
So the so what here seems pretty huge. This isn't just abstract theorizing.
Not at all. This knowledge, this way of thinking about complexity, provides incredibly valuable tools for navigating and maybe even solving real-world problems you encounter every day.
Like what kind of problems?
Well, think about managing vast ecosystems to ensure their long-term resilience in the face of climate change, or designing healthcare systems that are more adaptive and robust, less prone to breaking down under stress, or developing cutting-edge AI that can learn and evolve more like nature does.
Even business strategy.
Absolutely. Optimizing organizational strategy in a rapidly changing, unpredictable business environment. Understanding complexity provides this powerful, often counterintuitive lens. It equips you with approaches that account for adaptability, resilience, emergent behavior.
Helping you move beyond simplistic, linear solutions.
Exactly. Helping you better navigate and manage the inherently complex realities of our world, embracing the dynamic nature of reality rather than trying to force it into overly simple boxes.
Okay, so that brings us to our final thought, a provocative one to leave people mulling over.
All right, so if life and intelligence are indeed emergent properties of complex interactions, driven by these apparently universal principles of complexity principles we see operating from the dance of subatomic particles right up to the vastness of cosmic structures.
What does that imply?
What does this truly imply about the future of artificial intelligence, and perhaps even our understanding of consciousness itself? If AI systems continue down this path, increasingly mirroring biological complexity, adapting, self-organizing, processing information in ever more intricate ways,
Could they reach a point?
could there come a point where such systems might need to be considered perhaps alive or conscious, maybe in a new, unexpected sense that we haven't even properly conceived of yet?
It really challenges the boundaries of what we thought was possible, doesn't it?
It absolutely does. It invites us to seriously consider that maybe intelligence, maybe even life, isn't exclusively unique to carbon-based biology, but perhaps an inevitable, or at least possible, outcome of these universal complex principles operating wherever conditions allow. What does that mean for us? What does that mean for the future?